Hi everyone and welcome to another episode of Moyo Map. Today we'll be looking at the metric system and geometric shapes as we prepare for the CSEC exam in May of 2025. So we want to ensure that we have that full grasp and understanding of questions that falls under this topic. So in today's exercise we'll be looking at scales and measurements, perimeter and area of shapes, volume of solids, circumference of the circle, area of the circle. We'll be looking at sectors and questions involving circle theorems. So let's begin by looking at scales and measurements. So the first question, write the following scales in the form 1 to x. So 1 to x. And we have here 1 millimeter is equal to 1 meter. So of course with scale, questions involving scale reading, what we need to do, this 1 to x, it simply means if we're dealing with 1 millimeter, this will be 1 millimeter on the map, and how much that 1 millimeter is equal to in real life, actual life. So if 1 millimeter is equal to 1 meter, how much is 1 millimeter equal to in actual life? So it means that 1 meter is equal to how many millimeters? So if 10 millimeters is equal to 1 centimeter, we know that 100 centimeters is equal to 1 meter, and therefore 1,000 millimeters, if I multiply 10 by 100, 1,000 millimeters will be 1 meter. So 1 meter is really equal to 1,000 millimeters. We can say 1 millimeter, this is on the map, is equal to 1,000 millimeters in actual life. And therefore we can state the ratio as 1 to 1,000. Alright, so that's part 1. Let's look at part 2. Part 2, also again 1 to x, and we have 2 centimeters is equal to 6 meters. Again, we want to show what is on the map, what is that compared to in real or actual life, right? So we know that 2 centimeters, let's break it down to 1 centimeter. So if I divide both sides by 2 centimeters divided by 2, 6 meters divided by 2, 1 centimeter is equal to 3 meters. So it's always important to break it down to 1 centimeter, 1 millimeter, 1 meter, what happens. So if we have 2 centimeters is equal to 6 meters, we want to simplify that to 1 centimeter, which in this case is equal to 3 meters. So 3 meters is equal to how many centimeters? So we know that if 100 centimeters is equal to 1 meter, or would we write it the other way around? If 1 meter is equal to 100 centimeters, then we know that 3 meters will be 3 times 100, which is 300 centimeters. So we know 3 meters is equal to 300 centimeters. So we can simply write this as 1 centimeter on the map is really equal to 300 centimeters in real life, the actual. So we can state our ratio as 1 to 300. This simply means 1 centimeter on the map is equal to 300 centimeters in actual life. Alright? So let's move on to another So we have this question here. It says here, determine in centimeters the distance from Q to R. So the distance from Q to R here, 1 in centimeters will be 1, 2, 3, 4, 5, and that's 6 centimeters. Because if we read the question, it says the map shown below is a grid, is drawn on a grid of 1 centimeter squares. So it means that each side of the square is equal to 1 centimeter. P, Q, R, and S are 4 tracking stations. The scale on the map is 1 to 2000. So you want us to determine the distance from Q to R. So we have each length of the square is 1 centimeter. So that's 1, 2, 3, 4, 5, 6 centimeters. Alright? So we know that QR is equal to 6 centimeters. And then they want us to determine by counting the area in square centimeters of the plane PQRS on the map. So by counting, so if you're counting, normally when we are counting squares that are a half or more than a half in size is considered 1. So this here looks like it's more than a half, so we can consider that to be a 1 centimeter square. This is another 1 centimeter square, so we have 1, 2, 3, 4, 5, 6. This is more than a half, so it's considered a 1 centimeter square. This is 7, 8, 9, 10, 11. This is more than a half, 12, 13, 14, 15. This is less than a half, so we consider 16, 17, 18. So we're going to have here, so by counting, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so once we have a square that is a half or more than a half, it's considered a 1 centimeter square. And therefore, this is considered 1, this is considered 1, this is considered 1. Alright? So therefore, we will have here determined by counting the area in square centimeters of the plane PQRS on the map. So by counting, this will be 18 square centimeters. So that's part 2. Let's look at part 3. So they want us to calculate the actual distance in kilometers between Q and R. So what that actual distance in kilometers between Q and R, the actual distance. That means the distance in real life. This is the distance on the map, but what is actually the distance in real life? So part 3. So we know 1 to 2000 simply means 1 centimeter on the map is equal to 2000 centimeters. This is on the map, and this is 2000 centimeters in the actual. Alright? So therefore, we know that if we have to determine what is the actual distance in kilometers, of course, this here it is 6 centimeters on the map. So 6 centimeters in the actual will be, so 6 centimeters on the map in actual will be 6 by 2000, which is 12,000 centimeters. This is an actual, right? So we want to now determine what is the actual distance in kilometers. So this is the actual distance in centimeters, but we have to now convert that to kilometers. So we have to know how many centimeters is in a kilometer. So we know that 10 millimeters is equal to 1 centimeter. We know that 100 centimeters is equal to 1 meter, and 1,000 meters is equal to 1 kilometer. So for us to determine how many centimeters we have in a kilometer, We're going to multiply 100 by 1,000, which is 100,000 centimeters is equal to 1 kilometer. Alright? So, we want to now determine how much is 12,000 centimeters in, what is that in as a kilometer? In terms of kilometers. So we will have 1 centimeter is equal to 1 over 100,000 kilometers, and therefore 12,000 centimeters, which is your actual, yeah, in kilometers will be equal to 1 over 100,000 by 12,000, which will simplify to 3 zeros go, 3 zeros go. I can say 4 into 12 is 3, and 4 into 100 is 25. So this will give us 3 all over 25 kilometers. So the question asks, calculate the actual distance in kilometers between Q and R. So the actual distance between Q and R is 3 all over 25 kilometers. Alright, now calculate the actual area in square meters of the plane P, Q, R, and S. Alright, so you want the actual area in square meters of P, Q, R, and S. So let's calculate the actual area. So I'm erasing here. So for us to calculate the actual area in square meters of PQRS, now previously we saw where the area by counting in square centimeters of PQRS, we got that to be 18 centimeters squared, right? So they want us to calculate the actual area of the plane PQRS in square meters. Okay? Now, we know that 1 centimeter is equal to, on the map, is 2,000 centimeters. This is your actual. Yeah? So we know that 1 square centimeter, which is 1 centimeter by 1 centimeter, will be 2,000 centimeters by 2,000 centimeters. So 1 square centimeter is equal to 6. So 1 square centimeter is equal to, this is on the map, is really equal to 4 million square centimeters in real life. That's your actual. So what we want to do is to determine the actual area in square meters. So the actual area on the map in centimeters is 18 centimeters squared. So therefore the actual area in real life, this is the actual area on the map, it's 18 square centimeters, then the actual area in real life of that shape will be, if 1 cm squared is equal to 4 million cm squared in the real life or actual, then 18 cm squared on the map will be equal to 18 times 4 million cm squared. What is 18 times 4 million? That will give us 18 times 4, 1, 2, 3, 4, 5, 6. Right, this will give us 7, 2, 1, 2, 3, 4, 5, 6. 72 million cm squared, right? So this is the actual. So 18 cm squared on the map is equal to 72 million cm squared in real life, actual. But remember, the question asked us to determine the area of PQRS, that shape, in meter squared. In meter squared, not centimeter squared. So we can't leave one answer like that. So we have to represent it in meter squared. So we know that 100 centimeters is equal to 1 meter. Good? So therefore 1 centimeter is equal to 1 over 100 meters. And therefore 1 centimeter squared, 1 centimeter squared, right? 1 centimeter squared is equal to 1 over 100 times 1 over 100 meters squared. So 1 centimeter squared is equal to 1 all over 1, 2, 3, 4 meters squared. So if 1 centimeter squared is equal to 1 all over 10,000 meters squared, then 72, we converted from centimeter squared to meter squared, and this is our relationship to help us to convert from centimeter squared to meter squared. So therefore 72 million centimeter squared will be to multiply 1 all over 10,000 by 72 million. And this will help us to convert into meter squared. So this will be 1, 2, 3, 4, 1, 2, 3, 4. So this will give us 7200 meters squared. So this is how much 18 centimeters squared on the map, how much that is equal to in meters squared in real life, the actual. Alright? So it's important to know these conversion relationships. Alright, let's move on to another question. So the other question, let me erase. So the diagram below shows a map of a golf course drawn on a grid of 1 square centimeters or centimeter squares. The scale on the map is 1 to 4,000. So we have our 1 centimeter squares, and the scale on the map is 1 to 4,000. 1 to 4,000 means 1 centimeter. This is 1 to 4,000. It simply means 1 centimeter on the map is equal to 4,000 centimeters in the actual. Right? Real life. So, using the map of the golf course, find the distance to the nearest meter from South Gate to East Gate. So this is South Gate and this is East Gate. Remember, we have 1 centimeter square, so these are 1 centimeter square, meaning each side is equal to 1 centimeter. So the length of each side of the square is 1 centimeter. So this is 1, 2, 3 centimeters. So the distance from South Gate to East Gate, 1, is equal to 3 centimeters. This is from South Gate to East Gate. Now that's on the map. But they want the distance, of course, in meters, meaning they want that distance in real life. Yeah? So For us to determine that distance in real life, we know that first, this is 3 centimeters on the map, but we have to convert that 3 centimeters to your measurement in actual or real life. So how do we do so? So if 1 centimeter on the map is equal to 4,000 centimeters in actual, then 3 centimeters on the map in actual will be 4,000 times 3, which is equal to 12,000 centimeters in actual. So 3 centimeters on the map is really equal to 12,000 centimeters in actual. But they want us to represent the answer to the nearest meter. So it means we have to represent our answer in meters. So let us do so. We know that if 100 centimeters is equal to 1 meter, we're converting it into meters now. We know that 1 centimeter is 1 all over 100 meters. And therefore 12,000 centimeters. So we convert in this distance here from Southgate is given actual into meters. So this is in actual in centimeters, so let's convert the actual into meters. So therefore 12,000 centimeters will be 1 all over 100 times 12,000, which is 120 meters. Yeah, so this distance from Southgate to Eastgate in meters is 120 meters. Let's look at part 2. The distance in meters from Northgate to Southgate. So you want this distance from Northgate to Southgate. So to get our distance from Northgate to Southgate, what we can do is we can draw a line from here to here. We can get that measurement. So that measurement will be 1, 2, 3, 4, 5. So that's 5 centimeters. And this will be 1, 2, 3 centimeters. And what we can do here, we have a right angle triangle. So we can use Pythagoras' theorem to help us to determine that distance from Northgate to Southgate. So let us use Pythagoras' theorem. So using Pythagoras' theorem to help us to determine what is the distance from Northgate to Southgate, and of course that distance will be in centimeters on the map. So using Pythagoras' theorem, we can state, Pythagoras is the hypotenuse. We can say the hypotenuse squared, which I'll call it x. This is x squared, is equal to the sum of the squares of the other two sides. This is 5 bracket squared plus 3 bracket squared. So this will give us x squared, this is part 2, is equal to 25 plus 9. X is equal to 34. X squared is equal to 34. And therefore x is the square root of 34 centimeters. So we know that the distance between Northgate and Southgate is the square root of 34 centimeters, which we can work on our calculator. This is the second function, square root 34. Right, so we're going to get 5.83 centimeters are represented to 3 significant figures. Alright, so that's the distance from Northgate to Southgate. But they want that distance in meters. So this here is your distance on the map. And if it's in meters, it means they want that distance in actual, right? In meters, of course. So for us to do so, we know that if 1 centimeter on the map is equal to 4,000 centimeters in actual, therefore 5.83 centimeters on the map, which is this distance from here to here, is equal to how many centimeters in actual? So it will be 5.83 times 4,000, which will give us, this will give us 23320 centimeters in actual. Alright? So we want to now represent this measurement or that distance in meters. So we have to convert from centimeters to meters, and this is where we use our conversion relationship. 100 centimeters is equal to 1 meter. So therefore 1 centimeter is equal to 1 all over 100 meters, and therefore 23320 centimeters will be equal to 1 all over 100 times 23320. And when we divide that by 100, this will give us 23320 divided by 100 will give us 233.2 meters. And this is how much the distance from North Gate to South Gate, how much that is equal to in meters in actual. Alright? Now let's look at part 3. Right. So the area on the ground represented by 1 centimeter squared on the map. So the area on the ground. So for us to calculate the area on the ground represented by 1 centimeter squared on the map. So that will be what? So the area on the ground. So we know that 1 centimeter is equal to 4,000 centimeters. This is on the map. And this is on the ground. So we know that if this is the map and that's the ground, then 1 centimeter squared, which is 1 centimeter by 1 centimeter, on the map will give us what on the ground. So the area on the ground is represented by 1 cm squared on the map. So this will be 4 times 4. This is so 1 cm squared is equal to 4 by 4, that is 16,000,000 cm squared. Right? So that is what that is equal to on the ground. So 1 cm squared on the map is equal to 16 million cm squared on the ground. So this is on your map, and this is the ground. Yeah? So the area on the ground is represented by 1 cm squared on the map, and that is what it is equal to with 1 cm squared on the map. Yeah? So that is what that is equal to. Now they want the actual area of the golf course, giving your answer in square meters. Now the actual area of the golf course. So the actual area of the golf course will be this region here, and what we'll have to do is to count the squares for us to determine what is the actual area of the golf course. Yeah, so we have to count those squares, and to count the squares, this will give us what? Now remember, any square that is greater than a half or half and more is considered 1. So this case is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This looks a little less than half. This is 21, 22, 23, 24, 25, 26, 27. So the actual area of the golf course, on the map, it is, so the area of golf course on map is equal to 27 centimeters squared. But they want the actual area of the golf course. Yeah? So what's the actual area of the golf course? Given your answer in square meters. Okay? So we know that if 1 centimeter squared, so we calculated this previously, is equal to, on the map, is equal to 60 million cm squared on the ground, then we can determine what is 27 cm squared on the map. What is that equal to in cm squared on the ground? So you can do that by simply saying 1 cm squared is equal to 16 million cm squared. Then we know that 27 cm squared will be, that will be 16 million multiplied by 27. When we multiply 60 million by 27, that will give us right, this will give us 4, 3, 2, 1, 2, 3, 4, 5, 6 centimeters squared on the ground. So this is what 27 cm squared on the map. This is what it's equal to on the ground. But what we want to do is to convert that now into meter squared. So we know if 100 centimeters is equal to 1 meter, right? Then we know that 100 by 100 centimeters by 100 centimeters is equal to 1 meter by 1 meter. So we know that we know that 10,000 centimeters squared is equal to 1 meter squared. So therefore, if 10,000 centimeters squared is equal to 1 meter squared, then 1 centimeter squared is equal to 1 all over 10,000 meters squared, and therefore 432 million centimeters squared, what that is equal to meters squared, will be 1 all over 10,000 times 432. So 1, 2, 3, 4, 1, 2, 3, 4. So this will give us 43200 meters squared, but the actual area of the golf course in meters squared. This is the actual. Alright? Or the ground. Alright? So the area of the golf course, we determined that to be 27 centimeters. That's on the map by counting squares. So what we have to do is to convert this 27 centimeters squared on the map into that area of 27 cm squared on the map. We have to convert that into the area on the ground. Alright? And of course, using your relationship, we know that if 1 cm squared is equal to 16 million cm squared, because 1 centimeter on the map is 400 cm squared on the ground, then 1 cm by 1 cm on the map, which is 1 cm squared, it's 400 by 4,000 by 4,000, which will be 16 million cm squared on the ground. So therefore, we can easily convert our 27 cm squared on the map into the area in cm squared on the ground, and therefore we converted this area from cm squared on the map to meter squared. Alright? Using our relationship, 100 centimeters is equal to 1 meter, so 100 by 100, which is 10,000 cm squared, is equal to 1 meter squared. So therefore we can determine that 1 cm squared is equal to meter squared, which is 1 over 10,000, and therefore 432 million cm squared in meter squared is equal to what we have here. So that's the actual. Alright. So, right, so let's look at another question. Let's look at one more question showing scale and measurements, because this often gives students some challenges. So we want to make sure that we're clear in terms of conversions, ensure that we understand when they talk about the map as opposed to the actual, and showing the relationship to conversion from one unit to another is very important. So let's look at this last one here. So the diagram below shows a map of an island drawn on a grid of 1 centimeter squared. So these are 1 centimeter squares. The map is drawn to a scale of 1 to 50,000. 1 to 50,000 means 1 centimeter on the map is equal to 50,000 centimeters in actual. Alright? Real life. So they want us to copy and complete each of the following sentences. So we have 1 centimeter on the map represents how many centimeters on the island. So this actually will be your island. So 1 centimeter, so this will answer the question right here. 1 centimeter on the map represents 50,000 centimeters on the island. So this is your map, and this is your island. That's part 1. And 2, an area of 1 cm squared on the map represents an area of how many cm squared on the island. So this will be, if 1 cm on the map is 50,000 cm on the island, then we know if 1 cm by 1 cm, which will give us 1 cm squared, on the map will be 50,000 by 50,000 on the island. So this is 50,000 cm by 50,000 cm on the island. So 1 cm by 1 cm will give us 1 cm squared, and this is 5 by 5 is 25. We're going to have 1, 2, 3, 4, 5, 6, 7, 8 zeros. Centimeters squared, right? So 1 cm squared on the map represents an area of, that looks like about 3 and 3, 6. That looks like about 2.5 billion, right? Cm squared on the island. So let's look at part 3. Given that 1 kilometer is equal to 100,000 centimeters, a distance of 1 centimeter on the map represents a distance of how many kilometers on the island? So given that 1 kilometer is equal to 100,000 centimeters, so a distance of 1 centimeter on the map represents a distance of how many kilometers on the island. Alright, so if 1 kilometer is equal to 100,000 centimeters, therefore a distance of 1 centimeter on the map. Okay, so we know that if 1 centimeter on the map is equal to 50,000 centimeters on the island. Okay, because they want to know what 1 centimeter on the map represents a distance of how many kilometers on the island. Okay, so 1 centimeter on the map represents 50,000 centimeters on the island. Okay, so we want to convert this 50,000 centimeters into kilometers using this relationship we have here between kilometers and centimeters. So we know that whatever you have to convert to always goes on the right of the relationship. So 100,000, so I'm going to switch it from 100,000 centimeters is equal to 1 kilometer. I know that 1 centimeter is equal to 1 all over 100,000 kilometers. 1 centimeter is equal to that. And therefore, 50,000 centimeters. Because I want us to determine what is the distance in kilometers of 1 centimeter on the map. And what is that distance in kilometers on the island? Yeah? And we know 1 centimeter on the map is equal to 50,000 centimeters on the island. So therefore 50,000 centimeters on your island is equal to how many kilometers? This is going to be 1 all over 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 multiplied by 50,000. So this will simplify to 4 zeros, 4 zeros, 5 and 5, 1, 5 and 10. So this will give us half of a kilometer. Alright? So given that 1 kilometer is equal to 100,000 centimeters, a distance of 1 centimeter on the map represents a distance of how many kilometers on the island. So the distance of 1 centimeter on the map represents 50,000 centimeters on the island. And and therefore we want to convert 50,000 centimeters into kilometers. So we use our relationship. 100,000 centimeters is equal to 1 kilometer. We find for 1 centimeter, which is equal to 1 over 100,000 kilometers, and therefore 50,000 centimeters will be 1 over 100,000 times 50,000 will give us half of a kilometer. Alright? So very important for us to note. Alright, let's look at the other part of this question. It says here, L and M are two tracking stations. State in centimeters the distance LM on the map. So L and M are two tracking stations. State in centimeters the distance LM on the map. So this is L and this is M. You have two tracking stations. And what you want us to do is to state in centimeters the distance LM on the map. So the distance LM on the map, this will be the distance LM on the map will be 1, 2, 3, 4, 5, 6, 7, 8. Right? So that's the distance LM on the map. Remember, each square is equal to what? The side of each square is equal to 1 centimeter because they're 1 centimeter squares. So you know that this is 1 centimeter. That's 1, 2, 3, 4, 5, 6, 7, 8. So for that part of the question, B part 1, that is going to be 8 centimeters. Part 2, calculate the actual distance in kilometers from L to M on the island. Right? So they want the actual distance in kilometers. So for us to determine this actual distance here in kilometers on the island, it means that we have to convert this 8 centimeters on the map to the number of centimeters that is required for the island. So what is this equivalent to with respect to the island? And for us to determine that, we know that if 1 centimeter is equal to 1 centimeter on the map is equal to 50,000 centimeters on the island, then 8 centimeters on the map is equal to how many centimeters on the island? That will be simply 8 by 50,000. And 8 by 50,000, this will give us 8 multiplied by 50,000. Right, this will give us 400,000 centimeters on the island. Alright? So 8 centimeters on the map is 400,000 centimeters on the island. But I want the actual distance in kilometers. So after we have converted our 8 centimeters on the map to 400 centimeters on the island, that's what it's equivalent to on the island. Let us now convert it into kilometers. So we know that if 100,000 centimeters, and we saw that previously, is equal to 1 kilometer, then 1 centimeter is equal to 1 over 100,000 kilometers, and therefore 400,000 centimeters will be, therefore 400,000 centimeters, let's convert that into kilometers. This will be 1 over 100,000 times 400,000 400,000 which will leave us with 4 kilometers. So that's, let me just double check here. 1, 2, 3, 4, 5, 6, 7, 8, right? So we have 8 centimeters. Yeah? So we can put that to 400,000. Yeah? So that's the actual distance in kilometers from L to M. Yeah? So that's 4 kilometers. So that's the actual distance. Yeah? So pretty straightforward. Let us now, let's look at part C. So part C, or if not, what we could have also done to make it much easier, we know previously we would have calculated 1 centimeter on the map is well equal to half of a kilometer in actual. We did that previously. So therefore, 8 centimeters will be to multiply a half by 8. Think about the same 4 kilometers. Right? It might have been easier to do. But this is a straightforward way we can put the 8 centimeters to the measurement on the island conversion to the island, which will be 400,000. And then what we can do is to determine how much 400,000 centimeters will be equal to kilometers. Right, the second part, C part 1. The area shaded on the map is a forest reserve. By counting squares, estimate in centimeters squared the area of the forest reserve as shown on the map. So the area of the shaded region on the map is a forest reserve. So let's see. So this is the shaded region here. And by counting squares, estimate in centimeters squared the area of the forest reserve as shown on the map. So what is a counting squares, right? So in counting squares, this looks like half of a square. So I'll count it in rows. So this looks like half of a square. And sometimes half is considered 1, right? But let's look at it. This is half plus, this looks like 1.5 plus, this looks like 2.5 plus, this is 1, 2, 3 plus 1, 2, 3 plus 1, 2, this looks like 2.5 plus this looks like 1.5 plus a half. So let's add up that and let's see what we're going to get. This here it is a half, 0.5 plus 1.5 plus 2.5 plus 3 plus 3 plus 2.5 plus 1.5 plus 0.5. So that will give us, so when they ask us to, by counting the squares, estimate in cm squared the area of the forest reserve as shown on the map. So the area of the forest reserve will be 15 cm squared. That's the area of the forest reserve on the map. Yeah? And they want us to now calculate in kilometers squared the actual area of the forest reserve. So they want us to calculate in kilometers squared the actual area of the forest reserve. So this is C part 1. C part 2. What is the actual area in kilometers squared of the forest reserve? Now, we learned previously that we learned 1 centimeter squared. We learned that previously is equal to half of a kilometer, or 1 centimeter squared is equal to half of a kilometer squared. I think we worked out that previously. Yeah, 1 cm squared is equal to half of a kilometer squared. Am I right? I think we worked that out previously. Alright, but you want us to calculate in kilometers squared the actual area of the forest, you see. Yeah? In kilometers squared. So we know that we learned 1 centimeter previously is half of a kilometer. I think that's what we calculated previously. So 1 centimeter is half of a kilometer. Therefore, 1 centimeter by 1 centimeter, which is 1 centimeter squared, is half of a kilometer by half of a kilometer. We try to make it as short as possible to calculate this second part here. We learned 1 centimeter is equal to half of a kilometer previously. Yeah? And therefore, 1 centimeter by 1 centimeter, which is 1 centimeter squared, is a quarter of a kilometer squared. Yeah? So therefore, 15 centimeters squared, we have to convert that to kilometers squared. If 1 centimeter squared is a quarter of a kilometer squared, therefore 15 centimeters squared will be to multiply 15 by a quarter. And when we multiply 15 by a quarter, 15 divided by 4, 4 3s are 12, 34 and 3/4 kilometers squared. Alright? So we learned this previously. 1 centimeter is equal to 1 centimeter on the map is equal to half of a kilometer in real life. We have to convert it into kilometers. We learned that previously. So you can go back to the video, and when you're looking at the video again, you will see where we were able to show 1 centimeter is half of a kilometer. So therefore 1 centimeter by 1 centimeter will give us 1 centimeter squared will be a quarter of a kilometer squared, a half by a half. And once you know this relationship, we can determine what is 15 cm squared, which is a quarter by 15 to give us 3 3/4. Alright? Okay, so let's look at right, so looking at perimeter and area of shapes, volume of solid, circumference of a circle, area of a circle, sectors. So let's look at this question. So looking at part A, calculate the length of RS. So we're going to find the length of RS. That's pretty straightforward. We know this is 8 meters. From here to here is also 8 meters. And if this is 2 meters and that's 8 meters, all I have to do is subtract 2 from 8 to give me RS as 6 meters. So I know RS, A part 1, RS is equal to 6 meters. And hence state X. So they want us to state X, so part 2, X will be pretty straightforward as well, because if this is 10 a rectangle, if this is 10 meters, I expect this length also be 10 meters. Same way, this is a rectangle, if this is 8 meters, we expect this length from here to here to also be 8 meters. So we know if this is 10 meters, and from here to here it's 6, RS is 6. All I have to do is to subtract 6 from 10 to give me X as 4 meters. Part B, calculate the perimeter of the entire floor. So the perimeter of the entire floor will be to add this length, which is 10. So the perimeter will be 10 plus 5 plus. So we look at the distance around, right? That's perimeter. So 10 plus 5 plus, this is 5, plus 2 meters plus 3 meters plus 8 meters. This will be 3 meters here. We calculated this to be 4 meters. X was 4 meters. So this is 10 plus 5 plus 2 plus 3 plus 8. This will be plus 3 meters. 4 meters plus 5 meters. So 10 plus 5 plus 2 plus 3 plus 8 plus 3 plus 4 plus 5. Let's see what we're going to get the perimeter of that shape to be. So this will be 10 plus 5 plus 2 plus 3 plus 8 plus 3 plus 4 plus 5 to give us 14 meters. Good? And they want the area of the entire floor. So the area of the entire floor, so we're going to find the area of A, and we're going to find the area of B. A is a rectangle, length by width. So the length here is 10, by the width which is 5, which will give us 50 meters squared. That's the area of A. Let's find the area of B. Area of B will be the length by width because B is also a rectangle. A and B are rectangles. B will be the length being 8, the width being 3. You're going to get 24 meters squared. And therefore, the area of the entire floor, will be to add 50 to 24, which will give us 74 meters squared will be the area of the entire floor. Alright? Part D, section A of the floor is to be covered, so this is section A here, is to be covered with flooring boards measuring 1 meter by 20 centimeters. How many flooring boards are needed to cover section A? So we know we got the area of section A, and if we know that one flooring board is measured as 1 meter by 20 centimeters. Now, we can't have different units, so we have to convert both to the same unit. So let's convert that 20 centimeters to meters. Yeah? And then what we will do is to find the area of one flooring board, and we're going to divide it into the area of A to determine how many flooring boards are needed to cover A. So, right, so you have your flooring boards. It measures 1 meter by 20 centimeters. We're going to convert 20 centimeters into meters. We know that 100 centimeters is equal to 1 meter. So 1 centimeter is 1 over 100 meters. And 20 centimeters will be 1 all over 100 times 20, which is 1 over 5 or 0.2 meters. Okay? So you know this will be 1 meter times 0.2 meters, which of course will be 0.2 meters squared. Will be the area of the flooring board. And therefore, for us to determine, looking at part D, this is part D, and for us to determine the number of flooring boards needed to cover section A, so number of flooring boards to cover section A will be simply to divide the area of your section A by the area of your flooring board. And 50 divided by 0.2 will give us 250 boards are required. Okay? So let's move on to the next question. The diagram below, not drawn to scale, shows a plan of a swimming pool in the shape of a rectangle and 2 semicircles. The rectangle has a dimension 8 meters by 3.5 meters. They want us to state the length of the diameter of the semicircle AEF. So this is your semicircle here, and you want the diameter. So the diameter of the semicircle is simply what? 3.5 meters. Because as I mentioned, the dimension of the rectangle, this is the length, and this is the width. So the length is 8 meters, the width is 3.5 meters, and that also represents the diameter of that semicircle. So part 1, diameter is 3.5 meters. This is the diameter of semicircle. Then we have part 2. Calculate the perimeter of the swimming pool. So we want the perimeter. Perimeter is distance around. So it means that we have two semicircles. We can bring both semicircles together to give us an entire circle. So we can find the circumference of the circle. The circumference of circle. And let's make sure we know to find the circumference of a circle. So we're going to use 2 by pi by r. That's the circumference of diameter by pi. We can use diameter by pi and 1, 2, or diameter by pi. Yeah, we already have the diameter there. So the circumference will be on diameter. So I use diameter by pi times 22 all over 7. Yeah? So let's look at 3.5 times 22 divided by 7 will give us 11 centimeters. That will be the circumference of the circle, which will be the two semicircles combined. And therefore, if we have to calculate the perimeter will be to add the two lengths of your rectangle to the circumference of the circle. So that is going to be 8 plus 8 plus 11. That's 8 plus 8 plus 11, which will give us 27 meters will be the perimeter of the swimming pool. Right, let's look at this question here. So testing our knowledge of area, perimeter. So they want us to find the diagram below not drawn to scale shows a wooden toy in the shape of a prism. So we know a prism is a solid. Then we have the same shape on either end, which is called a cross section. So this will have you see, we have the same shape on either end along its length. So that's a prism. The cross section A, B, C, D, E. Good. So this is our cross section A, B, C, D, E. F is the midpoint of EC, an angle BAC and angle BCA are both 90 degrees. 90 degrees, alright? They want us to find the length of EF, which is pretty straightforward. So to find the length of EF, see that F is the midpoint, it means that this perpendicular height will cut this base EC in half, which will tell us this triangle here is an isosceles triangle. And therefore, if this length here is 6 centimeters, this length from E to C is also 6, and it will be split into 2 equal lengths, split in half, 3 centimeters, 3 centimeters. So for us to find EF part 1 is simply 6 centimeters divided by 2, which is 3 centimeters, straightforward. Part 2, they want us to find DF. So to find DF of course falls within a right angle triangle, and we have, this is perpendicular height, so we'll meet the base EF at the right angles. So we have here a right angle triangle. This is 3 centimeters. This is 5 centimeters. So we can use Pythagoras, or use a 3, 4, 5 triangle. This will automatically be 4 centimeters, but let's work it out. This is what? Hypotenuse squared, pi squared is equal to the sum of the squares of the other two sides. This is 25 is equal to x squared plus 9. 25 subtract 9 is equal to x squared. 9 from 25 will give us 16 is equal to x squared, and therefore we can find x by finding the square root of 16, which is 4 centimeters. Okay? So look at df is equal to 4 centimeters. And then we want the area of the face, A, B, C, D, E. So we want the area of this face, A, B, C, D, E. So that face comprises of a triangle and a rectangle. It may look like a square, but look at this. If this is 5, this is 5, this is 5 centimeters. So that is a rectangle. Look at the dimensions to help you. Alright, so we know that part 3, to get the area of the face, A, B, C, D, E, that is equal to the area of the triangle plus the area of the rectangle. And the area of your triangle, you know that this has a perpendicular height. You have your base, so you're going to be base by perpendicular height all over 2, plus the area of your rectangle, this will be length by breadth. So your base will be 6. Your perpendicular height, this is your perpendicular height, which you just calculated to be 4. So this is 4 centimeters divided by 2. And this will be plus the area of your rectangle, the length is 6. The width of that is 5. So you know this is 6 by 4 is 24 divided by 2 will give us 12. And 12 plus 30 will give us 42 centimeters squared. With the area of your face, A, B, C, D, E. Straightforward. Area of perimeter of your shapes and figures. Alright, let's move on to the next. We have a sector. So this here is a sector, which is a part of or fraction of an entire circle. And they want us to, in the diagram below not drawn the scale, shows a sector of a circle with center O. Angle MON, which is this angle here, is 45 degrees. And ON, which is the radius of the sector, it is 15 centimeters. Calculate, giving your answer correct to 2 decimal places using pi as 3.14. The length of the minor arc. So the minor arc is this. From M to N. So to find the length of your minor arc, the minor arc is a fraction of the entire circumference. Alright? It's a part of your entire circumference. So therefore, the length of arc will be the circumference of a circle times, remember that is a fraction, so the fraction will be theta all over 360. So I'm taking the sector angle theta, 45 degrees, and I'm going to put it all over 360 to help me to determine what fraction is this length of arc of the entire circumference. Okay? So the fraction of the circumference. So the circumference is 2 by pi, 3.14. The radius is 15 by the sector angle, which is 45 degrees over 360 degrees. And I can simplify, when we divide 45 into 360, that's 8, so it means this is 2 by 3.14 by 15. This is 1/8 of the entire circumference. That length of arc is 1/8 of the circumference. When you work it out, you're going to get what? 2 by 3.14 by 15 divided by 8 will give us 11.775, and I ask you to express your answer to 2 decimal places. This will be 11.78 centimeters, will be our length of arc. And part 2, you want the perimeter of the figure. So your length of arc is 11.78 centimeters. Then the perimeter is distance around. We know that the 2 radii will be both 15, so the perimeter will be 11.78 plus 15, which will give us, this will be 11.78 plus 15 will give us 41.78 centimeters with the perimeter of the figure M1. And then we want the area of that sector. So how do we find the area of this sector? Again, this here is a fraction of the area of the circle. That sector is a fraction, it's a piece of a part of it. So for part 3, the area of the sector, it is pi r squared, that's the area of a circle, times theta all over 360. Theta over 360 will show what is a fraction of that sector of the entire circle. Right? So it's, in this case, pi 3.14. The radius is 15, so that's 15 by 15 by the sector angle, which is 45 degrees over 360 degrees, which will be 3.14 by 15 times 1/8. So this is 1/8 of the entire area of the circle. Yeah, so that's the fraction of that sector of the entire area. And when we work it out, we're going to get what? 3.14 times 15 divided by 8 will give us 88.3125. But we want our answer correct to approximate it correct to 2 decimal places. 88.31 centimeters squared will be the area of that sector. Alright? So let's move on to another. So, the figure below that drawn the scale shows a circle with center O. The radius of the circle is 21 centimeters and the angle HOK is 40 degrees. So we have, so let's pull it out so you can see that a bit clearer. This is your center. This is O, this is H, this is K, and they want us to find the area of the minor sector. This is 40 degrees. And they want us to find the area of the minor sector HOK. Remember, the sector is this slice of pizza. This is your sector here, which is like a slice of pizza, a slice of cake. Good? So, what we want to do is to find the area of our sector HOK. So, that will be area of sector. It is simply pi r squared by theta all over 360. You know that's the area of the sector. That's right, let's take a quick one. Right, so the area of the sector part 1, it is simply pi r squared, your sector, by theta over 360, pi 3.14 by the radius, which is 21 by 21 by theta, which is 40 all over 360. Remember, this sector is a fraction of the entire area of the circle. And of course, what they want us to use pi is 22 over 7. So I was going to look to see what they wanted to use pi as. So you know this will be 22 over 7 by 21 by 21 by 0.41, 0.369. This is 1/9. That's a sector of the entire area. And therefore this will be 7 into 7 is 1, 7 into 21 is 3, 3 into 3 is 1, 3 into 9 is 3, 3 into 3 is 1, 3 into 21 is 7. I'm going to multiply 7 by 22 to give us 154 square centimeters. Will be the area of that minor sector HOK. And then they want the area of the triangle. So the area of the triangle. So for us to find the area of the triangle, there's an important formula we use to help us to find the area of the triangle. It's not only base by height all over 2. So you must get familiar with this important formula to find the area of the triangle. So the area of the triangle, we're going to use this formula. So let me work it here. Let me see if we have to. Right, and we want the area of the shaded segment. Right, so the area of the triangle, I'll write it here. We're going to use this formula. Get familiar with this very important formula. When you have two lone sides and an included angle, this is 21 centimeters, this is 21 centimeters. So we have two lone sides and an included angle. Once you have that, two sides need to form that angle. The formula we're going to use for the area of the triangle is a half times side A multiplied by side B multiplied by sine the angle theta. This is your included angle. Always make sure your calculator is in degrees. Alright? So this will be a half times 21 times 21 times sine 40 degrees. So we work that out, we're going to get what? A half times, let me put the entire thing into my calculator, 0.5 times 21 times 21 times sine 40 will give us 141.73 centimeters squared. I'll put it to one decimal place. 141.7 centimeters squared to 1 dp. We'll specify it approximate in fact, normally they'll ask you to approximate correct to 3 significant figures. Let's approximate this to 3 significant figures. So I'll write the answer as, so I'm counting from the first non-zero digit on the left, 1, 2, 3. My third significant figure, I look at the number after, which is 7. 1 is 5 or more. I add 1 to my 1 to become 2. This is the 3 significant figures. So I've approximated the answer correct to 3 significant figures. And this is the area of the triangle, and get familiar with that formula. Then they want us to find the area of the shaded segment, which is this region here. And actually pretty straightforward. Once you know the area of the triangle, you know the area of the entire sector. All you have to do is to subtract the area of the triangle from the area of the sector to give us the area of the shaded region. So area of the shaded segment is equal to area of sector subtract area of triangle. And the area of the sector, we worked that out previously to be 154. Subtract the area of the triangle is what? 142. So 142 from 154 will give us 12 square centimeters. will be the area of the shaded segment. Okay? So let's get familiar with these circle questions. They like to bring these circle questions in the exam. And don't forget to like, share, and subscribe to the channel. Okay, let's look at another dealing with your solids. Right, so the diagram below, not drawn to scale, shows a prism, and this is a prism. A prism is a solid with the same shape on either end along its length. And clearly we have the same shape. Alright, so you have the same shape on either end along its length. Good? So that there is a prism. And it says here the cross section will be the end or face located on either end of your solid. So this is a cross section. The cross section WXY is a square of area 144 cm squared. Calculate the volume of the prism. So to find the volume of any prism, in this case, this prism is a cuboid. There's a standard formula for the volume of any prism. It is the area of a cross section, multiplied by the length of the prism. Now we know what's the area of the cross section. The cross section is a square, which is 144 cm squared. So they give us the area of the cross section. So what we have to do is to multiply 144 by the length, which is 30. And 144 by 30 will give us, you're going to get 4,320 cm cubed will be the volume of that prism. And then they want to, with the prisms, they ask you to determine what is the total surface area. So the total surface area of this prism, in fact, I should not have erased that. Let me put it back. So the total surface area will be to find the area of all shapes located on the surface of that solid. So you know that this is a square whose area is 144. Of course, the square opposite will have an area of 144 centimeters squared. So we already know that in terms of the total surface area of all shapes located on the surface, we already know that's 2 times 144, representing your squares. But you have a rectangle on this side, a rectangle on top, a rectangle on the other side, a rectangle at the bottom. And of course, we have to determine, we know the length of the rectangle, we don't know the width, but we can find the width of the rectangle because if this is a square, and we know the area of a square is what? Side by side, x by x. And the area of the square is 144. X by x is x squared. Alright, we have to determine what x is equal to 144. X is the square root of 144, which is 12 centimeters. So I know that the length of the side of a square, it is 12 centimeters. So we know that for each rectangle, this is 30 and this is 12. This is also 30 and this side is 12. This is also 30 and this side here is 12. And if you're looking at what's flat on the ground, this is also 30. So each of the rectangles will have a length of 30 and a width of 12. So we know that this will be plus 4 times 30 times 12. So 30 times 12, of course, will be the area of one rectangle. But remember, we have 4 of them. So we're going to multiply 30, the result of 30 times 12 by 4 sides. 4 sides. Yeah, to give us the area of those 4 sides that are of the same dimension. That's the reason why I'm doing this, I'm multiplying by 4, because all are of the same dimensions. There are 4 sides, 1, 2, 3, and at the bottom, flat on the ground, all of the same dimension. So the total surface area will be 2 by 144, which is 288, plus 30 times 12, 360 times 4, which is 1440. So when I add 1440 to 288, I'm going to get 1728 centimeters squared. Will be the total surface area of your prism, also known as a cuboid. Alright, let's move on to the next. This is also a prism, a cylinder. It is also a prism. There are 2 questions in the cylinder. This is also a prism. And they want us to, with your cylinder, this here is your cross section, because we have 2 of the same shapes on either end, along with the length or height. Good? So, they want us to determine part A. What is the radius of the cylinder? So the radius, if this is the diameter 12, then the radius will be half of that. So your diameter, your radius, sorry, will be half of 12, which is 6. So the radius is 12 divided by 2, which is 6 centimeters. And part 2, you want the circumference of the cross section. The cross section will be your circle, the ends, right? So the cross section, there is a circle, so you want the circumference of the cross section. So the circumference of your circle will be 2 by pi by r. 2 by pi, let's just use pi as 3.14, by the radius, of course, which is 6. We could have used diameter by pi, any one of the 2. So this will give us 2 by 3.14 by 6 will give us 37.68 centimeters of the circumference of the cross section. Alright? That is circumference of your circle. And then it states here, the rectangle shown below, not drawn to scale, represents a net of the curved surface of the cylinder shown above. The curved surface of the cylinder shown above. State the values of A and B. So, this is a rectangle, and if we take a rectangle and fold it, what do we get? We get a cylinder. And what a rectangle represents the curved surface area of your cylinder. Alright, so if I take A, this is A, and I fold A, it gives me the what? Circumference of the circle. So, state the values of A and B. A, part 1. This is B, part 1. A is the circumference of your circle, which we found previously to be 37.68 centimeters, that is A. And B, of course, would be height of the cylinder. So B is the height, and we know that the height of the cylinder, it is 8 centimeters. So B is equal to 8 centimeters. So, having found A and B, we want to calculate the area of the curved surface of the cylinder. So the curved surface area of the cylinder, part 2, so the curved surface area of cylinder will be the circumference of the circle representing A, that's in length, which is 2 pi r. This is the formula for the curved surface area, times B, which represents the height of the cylinder. So this will be 37.68, which is representing A, also representing the circumference of the circle, by B, which is the height, 8. And when we work that out, it's going to give us the curved surface area of your cylinder. This is 37.68 multiplied by 8, which is 301.44 centimeters squared. So that's the curved surface area of your cylinder. Alright? Then we have the part C of this question. If 0.5 liters of water is poured into the cylinder, calculate correct or 1 decimal place the height of water in the cylinder. So, part C, right, so part C, we have our cylinder. We pour 0.5 liters of water. Let's assume that this is 0.5 liters of water. And we want to determine what is the height. Okay? So first, it's important for us to know what is, or recognize what is 0.5 liters in cm cube. So we can determine what is the volume of water in cm cube. Alright? And it is important for us to note that 1 liter is equal to 1,000 cm cube. Very important to know this conversion. So 1 liter is equal to 1,000 cm cube. So 0.5 liters will be 1,000 times 0.5. And 0.5 by 1,000 will give us 500 cm cube. So 500 cm cube of water when poured into that cylinder will give us a height of what? So again, the volume of a cylinder is area of the cross section times the height. So volume is what? Area of the cross section, and the cross section is a circle, which is what? Pi r squared times the height. Remember, that's a standard formula for any prism. This is a prism. It's the area of the cross section. The cross section in this case for a cylinder is a circle, pi r squared times the height. Okay? So we know that the volume, 0.5 liters, which is the same as 500 cm cube, right? When poured into the cylinder, whose area, of course, is pi r squared times the height, and let's determine what the height is equal to for a volume of 500 cm cube. This will be 500 is equal to, they asked us to use pi previously as 3.14, so it's going to be 3.14 times the radius of our cylinder. We know it's going to be 6 centimeters, so that's 6 by 6 times the height. And let's work out what is the height for a volume of 500 cm cube. So this would be 500 is equal to 3.14 by 6 by 6, which is 113.04 times the height, and this will be 500 divided by, if I have to get the height as a subject, I have to divide both sides by 113.04, and 500 divided by 113.04 will give me a height of 4.423. They ask us to approximate to 1 decimal place, so the height is 4.4 centimeters, will be the height for 0.5 liters of water being poured into your cylinder. Alright? Okay, so let's look at another. This says also, so we can add any questions involving solids and finding the volume of those solids, which are most cases prisms. So the diagram below in this case shows a block of metal in the shape of a prism, because we have the same shape on either end along its length or height. So that is a prism. The cross section of the block is a trapezium, and I hope you know to find the area of a trapezium. PQRS. With parallel sides PR and PS, and PQ, the perpendicular distance between the sides. Remember, a trapezium looks like this. You have two parallel sides and you have a perpendicular height. So it looks like that, or you can see a trapezium look like this sometimes. Two parallel sides and your perpendicular height. So they want us to calculate the area of the trapezium. So part 1, area of trapezium is a half times the sum of the two parallel sides by the perpendicular height. So you have the two parallel sides, which are 12 and 6. Two parallel sides, this is the A and B. So this is a half times 6 plus 12, and the perpendicular height, this is your perpendicular height, which will be 15. So this is a half times 18 times 15, which is 2 to 2, 1, 2 to 18 is 9, and 9 by 15 will give us 135 square centimeters will be the area of the trapezium. And given that ST, this is ST, is 3 centimeters, calculate the volume of the metal block. So the volume will be easy. Remember, this is a prism, and the volume of any prism is a standard formula. Area of the cross section, which we just found, the area of the trapezium, multiplied by the length or height. So the volume is area of cross section multiplied by height, or length, any one of two. And the area of the cross section, we're going to be 135 times the height, which is 3. So when we work that out, 135 by 3 will give us 405 cm cube. And don't forget it's volume, so the unit will be cube units, right? And the last part of this question, if the block of metal has a mass of 1.5 kilograms, calculate in grams the mass of 1 cubic centimeter of metal. 1 cubic centimeter of metal. So this metal block has a mass of 1.5 grams. Good? So calculate in grams the mass of 1 centimeter of metal. 1 centimeter cube of 1 cubic centimeter, sorry, of metal. So we know that if part 3, let me write part 3 here. If 405 cm cubed is equal to 1.5 kilograms, what will calculate in grams the mass of 1 cubic centimeter? Calculate in grams. It means we have to convert 1.5 kilograms to grams. And we know that 1,000 grams is equal to 1 kilogram. Yeah? So therefore, we have to determine what 1.5 kilograms is equal to grams. Remember what you have to convert to always goes on the right. 1 kilogram is equal to 1,000 grams. And therefore 1.5 kilograms will be 1.5 by 1,000. So 1 kilogram is 1,000 grams. Then 1.5 kilograms will be 1.5 times 1,000, which will give us 1,500 grams. Yeah? So if we have to determine what 1 cubic centimeter is equal to, we're going to change this now from 1.5 kilograms to 1,500 grams. Yeah? And therefore 1 cubic centimeter will be 1,500 divided by 405. And 1,500 divided by 405 will give us 3.7. Did they ask to approximate? Nope. So I'll put it to 3 significant figures. So the 3 significant figures I count from the first non-zero digit from the left, 1, 2, 3. I look at my number after, which is straight less than 5, so my 0 stays as is. So it's going to be 3.70 grams. This is what 1 cm cube is equal to. Alright? Alright, so let's look at the next. Right, so we're going to quickly circle theorems. So with circle theorems, it requires us to know our theorems. So you have to know our theorems in order for us to answer these questions competently. Right? So calculate given reason for your answer the size of each of the following angles. So you want to find angle M and L. M and L. So the letter in the middle is where the angle is located between the lines M N and L N. So you want to find this angle here. So to find that angle, we are going to use this important theorem. Theorem is this. You have a circle and you have this arc. Alright? Let's call the arc AB. It subtends or creates this angle at the center. This arc here creates this angle at the center, and this same arc creates an angle at the circumference of the circle. The same arc does that. Then the angle at the center is always twice the angle at the circumference, subtended by the same arc. So the same arc creates the angle at the center and it also creates the angle at the circumference. Once that happens, the angle at the center is twice the angle at the circumference. So we can say here part 1, angle MML, and we see here this is your arc from M to L. It creates the angle at the center and it also creates the angle at the circumference. Subtends, which means to create the angle at the center and creates that angle at the circumference. Subtends. So it's going to be 110 divided by 2. So angle M and L, 110 divided by 2 will be 55 degrees. Yeah? Part 2, angle LMO. Letter in the middle is where the angle is located between the lines LM and OM. This is the angle we're looking at here. So always with circle terms, I like to bring the isosceles triangle. This here is the center of the circle denoted by O, a line drawn from the center to the circumference, of course. Both are radii, 2 radii. They are equal in length, and therefore that triangle is isosceles. So therefore we know, and of course it's a given reason, right? So we have got to write the reason. The reason will be the angle at the center of the circle is twice the angle at the circumference of the circle subtended by the same arc. Right, so let's give you a reason. So part 2, angle LMO, simply use of the isosceles triangle. This is isosceles because the 2 radii are the same, and it means the 2 base angles are equal. So that's x and that's x. You know therefore to find angle LMO, which is this angle here, is going to be x plus 110 is equal to 180, and it's going to be 2x plus 110 is equal to 180. 2x is equal to 180 minus 110, and subtract 110 from 180 and divide by 2. That is 70 divided by 2, which will give us 35 degrees. So angle LMO is 35 degrees, and our reason will be base angles of an isosceles triangle are equal. Or you can just simply say for an isosceles triangle. Right? You get that as a reason. So you can surely understand what theorems you can recognize them. Let's look at another. Right, so in this diagram, the diagram we will not draw the scale shows a circle center O, lines BD and DCE are tangents. Tangents are lines that are drawn to touch on the circumference of the circle at given points called points of tangency, right? And it says an angle BCD, is 70 degrees. That angle we have there is 70 degrees. Then they want us to find angle OCE. Where is OCE? So look at the letter in the middle. So we're looking at OCE. This angle here we want to find. And to find angle OCE, it's straightforward. Part 1, we're using the fact that this theorem, we have a circle, center, radius, and this is a tangent. Then the angle between the radius and the tangent at the point of tangent is 90 degrees. So this is your radius, this is your tangent to that angle here. OCE is 90 degrees. So one angle OCE is 90 degrees. Okay? Of course, it asks a reason, but just know the angle between the radius and the tangent at the point of tangency is 90 degrees. Part 2, angle BAC. Where is BAC? BAC. Letter in the middle between BA and AC. This angle here. What is that angle equal to? Now, very important term we must note here. And this is a very common term that they bring in the CSEC exam. So if you have a chord and you have a tangent, this is part 2. A chord and a tangent. The angle between the chord and the tangent is always equal to the angle the chord subtends at the circumference. This is your chord and creates this angle at the circumference. So these two angles here will be equal. So if you look here, this is your chord from B to C. This is your tangent. So you have an angle between the chord and the tangent will be equal to the angle at the chord. The chord subtends. Look at both ends of the chord. Line drawn from B to A, line drawn from C to A. The chord subtends an angle at the circumference. So this angle here will be 70 degrees as well. This is 90 degrees, right? So we know that angle 2, angle BAC is equal to 70 degrees because of this important term. Let's look at 3. We have angle BOC. Angle BOC, where is BOC? This is BOC here. Alright, and again, this here is BOC is an isosceles triangle. You see that? From O to B is a radius, O to C is a radius, and that is an isosceles triangle. So what we can do is use the fact that if it's isosceles, the two base angles are equal. And therefore I can subtract or in fact no. Yeah, add the two base angles and I will subtract it from 180 to determine that angle. But what is the base angle equal to? Simply, this is a straight line, hence a straight angle. So I can add 90 to 70 and subtract it from 180. So 90 plus 70 will give me 160, and 160 from 180 gives me 20. So that's 20, then this will also be 20. And therefore I can say that angle BOC is equal to, these two both are 20. So I can say BOC it is 180, subtract 20 plus 20, 180 subtract 40, to give you 140 degrees. Good? And that's because it's an isosceles triangle, we can do that. And part 4, they want BDC. Where is angle BDC? BDC. This is the angle here. So to find BDC, what do we use? We're going to use the fact that we have a circle, and when we have tangents, meeting at an external point. Those are two tangents that meet at an external point. They are equal in length. Alright? They are equal in length. So these two tangents here are equal in length. And if they are equal in length, it means that this triangle DBC is an isosceles triangle. Very important terms. You have to know the terms in order to deal with this question. So therefore it's an isosceles, so it means that this is 70, this angle here is also 70 degrees. And therefore I can add 70 to 70 and I can subtract it from 180 to find the angle BDC. So angle BDC will be 180, subtract 70 plus 70, 180 subtract 140. So that angle there is equal to 40 degrees. Alright, so it's all about knowing your term. Alright, let's look at another. So, calculate the size of each of the following angles, given the reason for your answer. So, we want to find angle TPQ. TPQ, again, we're looking at the letter in the middle. So, between TP and PQ, this is the angle here. So, A angle TPQ, we're going to use the fact, this is the term we have to know. This is a circle, this is the center. This is a diameter. This is your diameter. Divide the circle in half. And if the diameter subtends an angle at the circumference, it subtends and creates that angle at the circumference, then this angle at the circumference is 90 degrees. So, A angle TPQ is equal to 90 degrees. Because angles in a semicircle is equal to, angles in a semicircle is equal to 90 degrees at the circumference, subtended by the diameter. Very important. Angles in a semicircle is equal to 90 degrees at the circumference of the circle, subtended by the diameter. So it must be subtended by the diameter. Let's look at B. Angle MTQ. MTQ. Let's see where that is located. M, T is in the middle. MTQ. So MTQ straightforward. Looking at this again. This is the center. If you have a radius or even a diameter, and you have a tangent, so the angle between the radius and the tangent, of diameter and the tangent, is equal to 90 degrees. So we know that angle MTQ is 90 degrees. Let's look at C, angle TQS. Now where's TQS? TQS. So look at here. TQ is the letter in the middle, so between TQ and QS. So we can draw a line from Q to S. So looking at this angle here. What is that angle equal to? And what we're going to see here is this. If you look, this is I'm using this term here. If I have my chord and I have my tangent, the angle between the chord and the tangent, you'll see the chord here, this is the chord TS, this is your tangent, this is the angle between the chord and the tangent, is equal to the angle that the chord subtends at the circumference. So this angle is equal to that angle. So the angle between the chord and the tangent, which is 23 degrees, is equal to the angle that the chord subtends at the circumference. So this is 23 degrees, then this angle here is also 23 degrees. So angle TQS is equal to 23 degrees. Because of that important term, the angle between the chord and the tangent is equal to the angle that the chord subtends at the circumference. And let's look at the last now, D angle SRQ, SRQ, SRQ. You can have this angle here. So what is that angle equal to? Right, now, if this is, now what will, the last D will be, and let me erase, I can put D on the board. So D will be, if I have a circle and I have a four-sided figure, where it's a quadrilateral where each vertex of the quadrilateral touch only the circumference of the circle, this quadrilateral is called a cyclic quadrilateral. And one of the terms of the cyclic quadrilateral is opposite interior angles. If this is A and this is B, this is C and this is D, the two opposite interior angles are supplementary, meaning they must add to give 180 degrees. Plus C plus D, when you add them. So if you know one, you can find the other. When you add them, you get 180. So look at what's happening here. I'm seeing a cyclic quadrilateral here. Cyclic quadrilateral, it is T, Q, R, S. You see, all four vertices touch the circumference of the circle. So we have a cyclic quadrilateral there. You see that, right? Four-sided figure. But they must, all vertices must touch the circumference. And if you look, if this is 23, this is 90 degrees, I can subtract 23 from 90. 90 subtract 23 will give you 67 degrees. This angle here is 67 degrees. Right? And if that's 67 degrees, then I can determine, if you look, I can use the fact that opposite interior angles are supplementary. If this is 67, these two are opposite interior angles. So I can subtract 67 from 180 for me to determine what is angle SRQ. So angle SRQ, SRQ will be equal to 180 subtract 67, and 180 subtract 67 will give me 130 degrees. And I can use the fact that opposite interior angles of a cyclic quadrilateral are supplementary. It's very important. You have to know your terms in order for you to answer these questions competently. This is 130 degrees. Alright, let's see. Alright, let's look at another. So, with circle terms, we have to also pay attention to lines that are parallel. When lines are parallel, we know that three important angles can come into play. The Z shape, which will be alternate angles, where this angle is equal to that angle, so that can come into play. You have your F shape. This angle is equal to that angle, corresponding angles. And then you have your box shape. This angle plus that angle is 180 degrees. That is known as co-interior angles. You have your two parallel lines here. Parallel lines. Co-interior angles. So when lines are parallel, you see these parallel lines in your circle term questions, know those angles can come into play to assist you. So let's see here. Calculate given reason for your answer, the size of angle PTS. Now where's angle PTS? P, looking at the letter in the middle, PTS. So looking at this angle here. So you want to find that angle. And what will that angle equal to? Now, so PTS. Now what we can do here is use the fact that, again, our parallel lines. So we see here parallel lines, and see where my Z shape can come into play, alternate angles. So if I look at the Z shape or parallel lines, alternate angles, this is 26, and this angle here is also 26 degrees. Okay? And if that is 26 degrees, it means that, of course, if you look, this triangle here is isosceles, not so? Because OS is a radius, OP is a radius, that triangle is isosceles. So this angle here is also 26 degrees. And what I can do, I can simply say, I can add those two angles and subtract it from 180 to get my angle at the center. So I can say 26 plus 26 from 180 will give me 128 degrees. And therefore, I can say now, I can use the theorem where the angle, the arc from P to S subtends or creates this angle at the center. So looking at part 1, this is what we're looking at here. Right, this is from P to S. It creates this angle at the center. So the arc from P all the way to S creates this angle at the center, which is 128 degrees. And the same arc from P to S creates this angle at the circumference, which is your T. So we can comfortably say now the angle at the center is twice the angle at the circumference subtended by the same arc. So we can say that angle PTS is equal to 128 divided by 2, which will give us 64 degrees. Yeah? And the reason is, of course, we use alternate angles. Tell us again the angle here is 26 within that isosceles triangle. And of course, the base angles will be equal, which will help us to find the angle at the center, which is 128 degrees. And we can use the fact that the angle at the center is twice the angle at the circumference subtended by the same arc. Very important. Now let's look at part 2. Angle RPQ. RPQ. Where is R? Looking at the letter in the middle between RP and QP. Looking at this angle here. That's angle RPQ. And that will be pretty straightforward because look at what's happening here. For RPQ, this is the center of my circle, the same center. From O to P is a radius. And this here is a tangent. So the angle between the radius and the tangent at the point of tangency, P is your point of tangency, the angle between the radius and the tangent at the point of tangency is 90 degrees. So this entire angle here is 90. So you can easily find angle RPQ by adding 26 to 26 and we subtract from 90 degrees to help us to find that angle RPQ. So RPQ will be 90 degrees, subtract 26 plus 26. 26 plus 26 will give us, that will give us 52. So we subtract 52 from 90, which will give us 38 degrees. So it's all about knowing your terms, being able to recognize those terms. Alright? Alright, let's look at, I think we have about 2 more. So let's look at 2 more, and that will bring us to the end of the session for today. So don't forget to like, share, and subscribe to the channel. We should tell everyone we know coming closer to exams, we'll be doing more and more sessions to help to prepare. Alright? So they want us to calculate angle PTR. So where's angle PTR? PTR. So we can add this angle here. So how are we going to find that angle? Part 1, using this theorem. Very common term I like to bring in the exam. If this is a chord, this is a tangent. The angle between the chord and the tangent is equal to the angle of the chord subtends at the circumference. So if this is your chord and that's your tangent, that's 46 degrees, then I know this angle here will also be 46 degrees because of that very important term. So I know part 1 angle PTR is equal to 46 degrees because the angle between the chord and the tangent is equal to the angle that the chord subtends at the circumference. Let's look at part 2. Angle TPR. So where's TPR? So you can have P, that's at the middle between TP and PR. You can have this angle here. So you want to find that angle, and automatically I see a big triangle. You see that big triangle? And you know that comes into play a lot, but the sum of 3 angles of a triangle must add to give 180. You want to find this angle here, let's call it X. So what I'm going to do is simply say here, X plus 46, that's one angle, plus 32 plus 46 is equal to 180. And I'm going to work out what X is equal to because I'm seeing a big triangle here. And the 3 angles of the triangle must add to give 180. This is your triangle, 46 plus X. So we're going to get here X plus 46 plus 46 plus 32 will give us 124 is equal to 180, and X is 180, subtract 124, X, that angle, which is the angle PTR, so that's 180, subtract 124, will give us 56. So I can say here, part 2, angle TPR is equal to 56 degrees. And basically, sum of 3 interior angles of a triangle is equal to 180. We have to give a reason. Alright, let's look at the last part of this. They want us to find angle TSR. Where is TSR? TSR, that's in the middle. So I'm looking at this angle here. And one time when I look at that shape, what do I see? I see now we got X to be 56. This is 56. And I automatically see, and I see a cyclic quadrilateral. I'm seeing a cyclic quadrilateral here. I'm seeing my 4-sided figure, part 3. So this is what I'm seeing. I'm seeing a cyclic quadrilateral. This is what I'm seeing. Right? We know opposite interior angles are supplementary. You must add to give 180. These two must add to give 180. So if we look at this, look at the cyclic quadrilateral. T, P, R, S. See the four-sided figure? Back, back, back. All vertices touch the circumference. So the opposite interior angles are supplementary. So therefore, I know for part 3, angle TSR will be 180 subtract 56. And 180 subtract 56 will give me 124 degrees. Straightforward. Alright? So let's look at, so this is 124. So let's look at the last question. Right. Determine the value of each of the following angles. Show detailed working where necessary and give reasons for you to support your answer. So they want us to find one angle PTR. Where is PTR? We look at the letter in the middle. PTR. We look at this angle here. Now, that theorem to help us to find that angle is this. So we have a chord which will divide your circle into two segments. Major segment, minor segment. And the chord subtends an angle at the circumference, right, in the major segment, and the same chord will subtend another angle at the circumference in your major segment. Like they have two horns, yeah? And once you see that occurring, then this angle is equal to that angle. So we're not seeing the chord, but we can have an imaginary chord here. You can draw an imaginary chord here, right? And if you look, the chord will subtend the angle at the circumference at T, and the same chord will subtend the angle at the circumference at B in the same segment. The chord divides the circle into two segments. So it means that angle PTR will be equal to 75 degrees. Because angles in the same segment are equal at the circumference subtended by the chord. Yeah? So angles in the same segment are equal at the circumference of the circle subtended by the same chord. And two, angle TPQ. TPQ. So looking at angle T, so this is 75 degrees. So TPQ, so looking at this angle in the middle, this angle here. That's angle TPQ. And one time I see a four-sided figure. I see bap, 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 bap. Four-sided figure where all four vertices touch the circumference of the circle. Yeah? And the opposite interior angle will be this angle here. So if I find this angle, I have to subtract that angle from the 180 to determine what is angle TPQ. So I'm seeing the cyclic quadrilateral. So the cyclic quadrilateral comes into play here. Right? So if I find this angle, I subtract it from 180 to find that angle. And this angle here is easy to obtain because it's a straight line, hence straight angle. So 60 from 180 will give me 120 degrees. Yeah? Or I can use another term for the cyclic quadrilateral. If I have an exterior angle, you can use one out of the two. This is the exterior angle, which is 60 degrees. The exterior angle, if you take one side and extend it, the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. So this is 60, this will be 60, or you can subtract 60 from 180 to give you 120, and opposite interior angles of a cyclic quadrilateral are supplementary. So this will be 120 from 180, 60. So either one of the two can be used. The exterior angle of a cyclic, because it's outside of, if you see the cyclic quadrilateral, it's outside of the cyclic quadrilaterals, the exterior angle is equal to the interior opposite angle. Yeah, so this is 60, this will also be 60. Or you can get this as 120 and subtract it from 180 to give you 60. So angle TPQ is equal to, I'll say 180 minus 120, 60 degrees. Alright? Okay, so this will bring us to the end of the session today. Please like, share, and subscribe to the channel. Make sure you tell all your friends to come and look at the channel, be a part of the sessions that have been held to prepare students for the CSEC examination. And I hope you review the videos to bring clarities to some of the topics and past questions that we're doing to help to prepare us for the exam in 2025 and of course beyond. Alright? So with that said, have a great evening, and I'll see you all in the next episode. Take care.